The goal here is to find the areas of the ratios between these two triangles. Now I left out all of the details needed because I want to ask you, what do you need in order to solve this problem? Right? What do you need in order to compare the areas in terms of a ratio? Well, of course, you would need the area. But what do you need to know area? Well, there are really two features given in a triangle, of course, the side length and the angles. So if I told you that this angle here was 90 degrees, and so was this, now you know they're both right triangles. And what if I told you that the hypotenuse of this triangle is 14, and that this leg over here is 4? Now you know a little bit more. You know one leg of the smaller triangle and the hypotenuse of the larger. But now if I give you that this is a 30-degree angle, right, and that this is also 30 degrees, you have enough information to solve the problem. You have side lengths and angles, and you can move forward. So even if you're stuck here, remember that you're either going to use the side lengths or the angles. And if they're giving you angle measurements, right, there's most likely a way to use those angles to your advantage. This is a special case of a triangle. It's the 30, 60, 90 degree triangle. And the 30, 60, 90 and the 45, 45, 90 are two special cases that I think you should be familiar with when dealing with trigonometry. Really quickly, we can prove what happens here. There's no need to really memorize these triangles or the special features of these triangles. To understand the 30, 60, 90, it's nice to draw an equilateral triangle, right? And then with an equilateral triangle, every side of that triangle is x, right? That's the definition of equilateral. And each angle measures 60 degrees, right? If we draw a vertical line here perpendicular to the base, right? If we draw an altitude, we get a right angle. And if we draw it so that it bisects this angle up here, right, we know that this measurement is now going to be 30 degrees. Bisects means cuts it in half. We also know that the length of this leg is half of the side, even though I drew it poorly. So if the side length here is x, right, this will be x over 2. But in fact, I think it might even be easier to call this side length x, which makes the original side length 2x, or double. All right, I'm just going to define it that way to avoid fractions. So the original side length of each side is 2x, and this half side is x. We want to know what is this leg right here, because essentially we've got this right triangle, right? We want to understand how this right triangle is defined. So then I'm thinking, well, maybe we shouldn't call it x and 2x. Let me clear it off. Maybe we should call it a and b, right? Clear that off. Oops, that eraser was too large. Undo that. Create a different eraser really quick. All right. Whoa, that was way too large. Okay. Apparently the eraser sizes I have here are not going to be helpful. So let me just go back to my pen. Sorry about that. This will be called, well, the original leg, let's call it A, right? So this leg over here, which is the hypotenuse, is 2A. That's the first great feature of your 30, 60, 90 triangle. The leg here that's across from the 30-degree angle, right, is half the length of the hypotenuse. So going back here, if our hypotenuse here is 14, we know that this leg, which is across from the 30-degree angle, is going to be 7. And now we can use the Pythagorean Theorem to find this third side. But a special property of the 30, 60, 90 is that this third side will always be equal to the shorter leg, 7, times the square root of 3. And we can prove that. So let's go back to this general example here. So this leg, we'll call it b. So using the Pythagorean Theorem, we know a squared plus b squared equals the hypotenuse squared, which is just 2a squared. Now 2a squared becomes 4a squared. We square both pieces there. This equals a squared plus b squared. To solve for b squared, we subtract a squared from both sides, right? What do we get? Well, b squared equals 3a squared. We want to know what b equals, and b equals, take the square root of both sides, the square root of 3 times the square root of a squared, which is just a. And there it is. This step here, this step right here, is saying that b always equals to the square root of 3 times a. And that allows us, right, to quickly find it. You could use the Pythagorean theorem there, but the area of this triangle is now going to be the base times the height divided by 2. And right here, we can call this our base, 7 radical 3 times our height of 7, right? So the area here will be what? Right up here. Area will be 7 times 7 radical 3, and that is just going to be equal to, 49 radical 3, right? 49 radical 3. So we do base times height, and that's being divided by 2, so this will be over 2. So we'll leave this in this form right now. I'm not going to reduce it until I see what happens here in this area. So reversing the logic, just quickly, if we know that this is a, 4 is a, the hypotenuse has to be double that, 8. And this needs to be 4 radical 3. So what does this area equal? Well, base is 4, or it doesn't really matter, I guess. As long as base and height are 2 dimensions perpendicular to each other or at a right angle, you're okay. But here we'll be consistent. This bottom leg, 4 radical 3, will be the base. So 4 radical 3 times the height, 4. Oh, let's get 9, let me fix that. Times 4 over 2. And that's going to equal 16 radical 3 over 2, which is just 8 radical 3. So they want to know what are the ratios of these two sides. Well, 49 radical 3 over 2, right, to 8 radical 3. And here, right, a ratio and a fraction are different, of course, in that they typically represent different things. This is a part-to-part relationship, which means one part of one triangle to another part. And that's best used, I think, in a ratio. But you can simplify ratios like we simplify fractions. And if that's hard to picture, just set it up into a fraction. This would be 49 radical 3 over 2, and that's over 8 radical 3, right? So to reduce this fraction, what would I do? Well, I would multiply both numerator and denominator by the reciprocal of 8 radical 3. So we get 1 over 8 radical 3, and I'll put my equal sign over here because it looks pretty shabby right there. Okay, and this equals what? Well, any number times its reciprocal is 1, and over here the radical 3's cancel out, and we get what? 49 over 16. 49 over 16. And can this be reduced? Well, what are the factors of 16? Factors of 16 are 1 and 2. But 1 doesn't help us. 2 doesn't go into 49. 3 doesn't go into 16. 4 goes into 16. And 8 goes into 16, right? But 4 doesn't go into 49. And 8 also does not go into 49. So here is your ratio right here. And if we go back, right, and we look at the scale factor between these two sides, what do you have to multiply 4 by to get 7? Let's look at that for a moment. 4 times x equals 7. Well, x would equal 7 divided by 4. That means that's the scale factor, right? These two shapes we're assuming are similar. So if you multiply each side by 7 over 4, you get its corresponding length. So another way to look at this problem, right, if you notice the connection here, the area is just x, or a scale factor. The ratio between the areas is equal to the scale factor squared. 7 squared is 49, 4 squared is 16, and this is a fundamental observation to make. If you multiply each dimension of a shape by a number, the area grows by the scale factor squared. A simple example would be if you had a little square or something and say 4 by 4. If you multiply each side by 2, right, you get an 8 by 8. You can almost see that it's certainly more than double in size, right? The area, in fact, will become 4 times larger. And again, multiply each side by 2, the area grows by the scale factor squared. That's another way of looking at this problem. Now, if you want, I'll also go through the 45-45-90 triangle proof really quickly. If not, I understand. We already talked about enough in this video. But in case it comes up, a 45-45-90 triangle. What's going to happen there with the sides? Well, assume that this length is called A. We could call this B, but in a 45-45-90 triangle, both legs are equal. So this could be B, but B is equal to A. So we'll just refer to it as A as well. And we still have our hypotenuse, C. So in this case, A squared plus B squared equals C squared, right? But we can think of that as A squared plus itself, because those two legs are equal. A squared plus A squared is 2A squared, and that equals C squared. So to solve for A squared, we could divide both sides by 2, and it equals A squared equals C squared over 2. What would A equal? We'll take the square root of both sides, right? And A would equal C over the square root of 2. But we usually rationalize the denominator there. Multiply both numerator and denominator by radical 2. And what do we get? Finally, we get radical 2 C over 2. What does that mean? Well, that means if you know what A is equal to, right, you can quickly find, right, the length of C. For example, let's say, or in this case, let's say C equals 2, right? What would A equal? Well, if you plug 2 into C, right, let's try that. Let's say I gave you a diagram like this. I say, oh, well, the hypotenuse here is 2. What are the two side lengths equal? Well, A here would equal, if you plug in the value for C, we would get radical 2 times 2 over 2. And that means the leg would equal radical 2. If we reverse that, and you're given, let's say, the length of the leg is 4 or something, we plug 4 in for A, and 4 equals radical 2 over 2C. And what would C equal? Well, to solve for C in this case, we multiply both sides by 2 as a first step, right? Times 2, times 2. These cancel out so far. Okay, so it equals 8. Radical 2 times C. And then we divide both sides by radical 2. And this actually works out quite nicely. So hang in there. Divide by radical 2. And now what? Well, these cancel out. Rationalize again. So here, radical 2 times radical 2 is 2. 8 over 2 is 4. And then it's 4 times radical 2, and that's equal to C. And this is usually the approach they give, which is if they give you a leg of 4, the hypotenuse is 4 radical 2 automatically. Right? That's usually the approach you'll get. They give you a leg on a right triangle, and say it's 4 or x or whatever. The hypotenuse is always going to equal that number times radical 2. But going back, if they give you the hypotenuse, right, you can use this generalization to work your way back to a leg. The hypotenuse, right, divided by 2 and multiplied by radical 2 is the leg. That's less useful, I think. And actually, usually you have to rebuild this proof every time if I need that relationship. But this one, I think, is a little bit more easy to internalize. In a 45-45-90, if they give you one leg, just multiply by radical 2 and you'll have the hypotenuse. Alright, hope this helped.